My boys, we have a wonderful machine in our possession, having until we fully explore the full potential of this miraculous machine. We shall tell no one. Welcome to the wonderful world of random sequencing. Today we're going to be covering a lot of different sequences, and we're going to start with this idea right here. And what we have is the number 7, and the 7 is equal to 111. And then binary notation, that is 7. And it also is associated to the 31, because the 31 carries the statement 111s, or 3 ones. So you have this, and this is the add statement. So it sees this as, and it's the 7 sees the 31 right here. But there is a statement here to add. So if you, as you see right here, we have 31 plus 21. That is equal to 51. Now over here we have a 31 plus 21, and that is equal to 51. Why? Because if this is 3 ones, 31 is 111, and this is 2 ones, which is right here, 2 ones. This says 2 ones is 1 1. So basically you're adding 3 ones plus 2 ones, that makes 5 ones. And over here the 30 is a bridge to the answer. So this is the more statement. And it goes to the 5, and now you know that there's going to be a 1 on the next sequence. Because this is 3 ones plus 2 ones, that's 5 ones. And you have your more statement, and then you have your 5, and automatically you already know there's going to be a 1 right there. And so what happens after that is you end up now with this statement called 7 ones. And 7 ones is this. It's the add statement. You have the add statement right there. And then you have 3 ones, that's 111. And then you have 2 ones, that's 1 1. So that's 5 ones. And if you add 2 more ones, that's 7 ones. And that answers right here, 7 ones. I wanted to go back to this statement right here where I have the 21 sequence to 11. Now the 21 carries the statement 2 ones. You see, 2 ones is 1 1. So this is a natural sequence right here. So I also want to express, go back to this 3121. Now I said that this 3121 is equal to 5 ones, or 15. In other words, if you were to represent that as a single cell, it would be 15. So this is another way of expressing the virtual 51, because there is no single cell that in Roulette that's 51. It's represented by 15. So if you go over here, you have the add statement right here, the plus, that's the add. Now 9 is the plus, it's the add statement. So you have 21 plus 31, and there's your add statement, and then this sequence right here is the C statement. It allows it to be, can I carry this sequence over, and diagonally it points to the 15, which is 51 in virtual memory. Now, I would suggest that if you know there's going to be a 5, at least a 5 of some sort, because in other words you have the 1 right there, so it could be a natural 5. So in this kind of situation, I would play all 5s, play 5, 15, 25, and 35. So that's the best way to answer these sequences, because you don't want to put just a 5. If you see a 1 and a 5 there, you think that's the answer, but it's not. Mother Nature throws curveballs, so go on, just play all 5s. That'd be 5, 15, 25, and 35. I wanted to talk about the concept 0, 0, 0, 0. That represents 4 zeros. Here's 1, 2, 3, 4. That you say 4 zeros, 4 zeros. And over here, as you can see, you have the 11, 10. Now that is a symbolic 40. It also could be a symbolic 70, because you have 111 in binary notation is a 7 linked to a 0, that would make 70. But in this case it's 40. And it usually repeats another 40 in a different way. And if you go just a half step this way, which happens to be the last place where you could express the 40, you'll see that on the left hand side we have the statements. It's 1 1. 1 1 is just the equal statement, just like that. And then it links to a 4 0. So in this situation where you think it's going to play out another 40, Well, the best way to play it out, it would be to play all fours. In other words, 4, 14, 24, and 34. If you play those, one of those is going to hit. In this case, it was 14. I'd like to talk about the concept 27. The 27 carries the statement 2 sevens, and that's equal to 7, 7. And 7 plus 7 is equal to 14. As you can see right here, we have a 2, 7. And we're looking for a 14, and it's carried by this 13, which the 13 carries the I am statement. It represents the I am. And so this click connects right here, and at this point it sequences downward to a 14. So these are basically equivalent statements right here. And another thing is that there are also the 27 can also represent itself right here as symbolically. In other words, what you have right here is an inverted 27, and the reason why that is because this 111 is 7, and this is a 2, so it makes an inverted 27, and it's followed by a equal sequence. This is the 3, which is the equal sign, and the 6 is the sequence statement, and it follows right through the 27, and so this is a relational sequence right here. I wanted to go back to this 27 I am and the 14. Sometimes you could verify whether it's a 14 or a 27 because they're relational. And what I do is I try to find a previous 14 in history, and that. And as you can see, there's no 14. So I use the 27 as a way to kind of verify whether it's a relational sequence. And what I do is I add these. You count from here to here. And so this line of sequences is 6, and this is 6, 7, 8, 9, 10, 11, 12. And if I see a number that has a 12 near the 27, I consider that to be a count number between this cell and this cell. And you could even do it with this cell right here. In other words, this is the 27, and so I'm wondering if the number is going to be a 27. If I believe that, all I have to do is count the distance between this cell and this cell. In doing so, if this is 6's, right, 6, 6, 6, that's 18, 19, 20, 21, 22. And if I see a 22, I don't see a 22 here, but I see a 22 right here. So this is the count number from this 27 to this 27. And that's one way to verify numbers. I want to talk about this sequence right here where we have the 0, 0. That is the C statement, as in seeing something. In this case, it sees the 36. And then it follows with the equal statement. So if it sees 36, it plays 36 again. So these are just, this is how you read these statements. C36 equals 36. I wanted to talk about the number 12 and what it represents. The number 12 is equal to 26, and the reason why is because 26 carries a statement 2 6's, and what is 2 6's? 6 6. 6 plus 6 is equal to 12. So as you can see right here, we start with the I am statement. This is the I am statement, and I am 12, and it's followed by a 6. The reason why it did that because it had a 2 right over here diagonally, and it makes 26. So 12 is equal to 26. Now, if you wanted to, I would recommend playing all 6's in this case, because if Mother Nature throws a curveball, then you have to be ready. And that would be 6, 16, 26, and 36. If you play any of those, you'll hit. In this case, it was the 6. So I am 12 is equal to 26, and you already have a 2 there, and it's going to be a 6. I would consider that the 6 as a high value, so you probably want to put more on the 6 there. I'd like to talk about the concept of 1100, and as you can see, there is 1100. What that represents is the number 26. The number 26 carries the statement 2 6's or 6 6, and what you see right there is a metamorphic 6. This is a 6, and this is a 6. So if you see an 1100 linked together, that's the number 26. And as you can see over here, we have a 2 6. That's 26. So 110026. Another thing I want to also mention is that these sixes can link sequence to twos. In other words, 2 plus 2 plus 2 is equal to 6. And this is a statement of the add statement. So it basically adds these numbers here, 2, 2, 2, which is 6. And this is an add statement. And as you can see over here, we also have 2, 2, 2, 2. That's represented as 4 2s. And so there is no cell that single number that's 42. It's represented by 24. So you have 2, 2, 2, 2, and then you have the equal statement. That's the 3 is equal to 11, which is the equal statement. And then they have the add statement, and then this is supposed to be 42, but it's represented by 24. I'd like to talk about the concept of 2, 2, 2, 2. Those represent 4 2s. This is 1, 2, 3, 4. Those are 4 2s. And the way that is represented by the 24 right here. In fact, over here we have the 3. The 3 in binary notation is 1, 1. So it represents the equal statement. So 4, 4, 4, 4 is 4 2s, and this is your equal signs, and it went to a 4, 2. Now, another reason why I went to a 4, 2 is because if you notice the 12, 14, on the left-hand side you have the 1, 1, that's the equal statement. Equals what? 24. And then you have the 19. The 19 represents a plus 1 or plus, and then it went into this 24 sequence right here. So again, we have the 1, 1, that's just the statement, equals 24. I'd like to also talk about this 36 sequence where this is 36 equals 36. Well, 36 plus 36 is equal to 72. There is no single number in roulette that's 72. It's represented by 27. So this is like a reverse 72. But so it's an equation. It says 36 equals 36 means to add the 36 plus 36, and that's supposed to be 72, which is represented by the 27. I wanted to talk about the 324 sequence. Now the 24 is the multiplier. If you were to go like ABC all the way to 24, you would get the X. So this is the multiplier. In this case, it uses itself as part of the equation. So 3 times 24 is equal to 72. Now the thing is there is no 72 in roulette. It's represented by the 27. As you can see right next door right here, we have the 27. So we've covered a lot of sequences here. I hope you enjoyed it, and we'll see you in the next sequence. And folks, as always, please click the subscribe button below, show some love, give me some thumbs up. I have links below with PayPal and Patreon, and I will see you on the next wonderful world of random sequencing.